Hi everyone! So this is a little mini lecture that is going to introduce you to part 2 of our 1.8 meaning of numbers assignment. And this is going to introduce you to a concept called the mole and molar mass. So really what we need to start out with talking about is what even is a mole. No, it is not the cute little furry animal that you might be thinking of that lives underground that has super poor eyesight. A mole is something actually completely different. So think about this. If I asked you to count a set of items, if I said, hey, put these into pairs, you would immediately know, oh, I need to put them in groups of 2 because you know that a pair represents 2 things. If I said, hey, go grab me a dozen donuts, you would know to grab 12 donuts because a dozen represents 12. And really, that's all a mole is. A mole is a chemist's counting unit. It's used to represent a certain number of things. So if I said, hey, get me a mole of this, you would know exactly how many things I was asking you to go grab. So when I say mole, only thing you need to know is that really it is a counting unit. It is a specific counting unit, so a pair represents 2, a dozen represents 12, a mole represents this many things. So the number that you would call this is 602 hexillion, and it's an insanely large number that you can see. It's got a ton of zeros on it, right? So let's put this in a little bit more digestible form, because if I asked you to write out this number a million times, which I'm going to ask you to do, it would take forever. So that's why we started learning about how to write things in scientific notation. It makes it a lot easier to actually represent this number. So in scientific notation, 1 mole is written as 6.02 times 10 to the 23rd things. You may also see it represented as 6.022 with an additional 2 on the end. It really depends on how many of those significant digits you're including in here, how accurate or how precise you want your number to be. But if I said, hey, go grab me 1 mole of pencils, you would bring back 6.02 times 10 to the 23rd pencils. The problem is, this is a bigger number than I'm sure you have ever encountered in your life. So let's see if we can try and put it into a amount of space, like how much space this would take up to kind of make it make sense. So take a second to pause the video and think. If I asked you to go grab 6.02 times 10 to the 23rd donuts, or 1 mole of donuts, how much space do you think that might occupy? Do you think this might be the size of our classroom, fill up our classroom? Do you think it might fill up the San Marcos campus, the football field, your house, the size of America as a country? So pause the video. How much space do you think this might take up? Make your little prediction. Okay, so if you said, oh, Miss Lambert, I think that's a really huge number of donuts. I think this is going to occupy the entire surface of the earth to a depth of 8 kilometers or 5 miles, you would be exactly correct. And I am highly doubting anyone actually said that as their answer, unless you ChatGPT'd it. But this is the amount of space that this many donuts, a mole of donuts would take up. And that's a huge amount of space, covering the entire earth to a depth of 5 miles. Incomprehensibly big. So let's do another one. Let's say that if you had 1 mole of basketballs, so 6.022 times 10 to the 23rd basketballs, you could create an entirely new planet made of basketballs that's the size of our Earth. Again, a ridiculously large number. One more. If you received a mole of pennies on the day you were born and you spent $1 million every second until the day you died at 100 years old, you would still have more than 99.99% of your money in the bank. So what does this tell us? It tells us that this is an inconceivable amount of things. It's such a ridiculously large number. But It is the number that chemists use. It is our counting unit. So why? Why do we care? Why do we use this number that's so insanely large? Well, think about the amount of stuff that we're working with. We're usually working with atoms or particles of these compounds or these substances, whatever we're dealing with, that are so incredibly tiny. You just learned earlier in this lesson, like a little bit of an appreciation, I hope, for the size of an atom. It's something that's so small, you can't see it when you look through a regular microscope. So that's why we have to use a number that's so insanely large, because these things that we're working with are teeny, tiny. So we got to use a number that's really big, because it's actually incredibly helpful. One thing you'll notice here is that I just have a bunch of other units of grouping for you. And underneath the mole, I also put Avogadro's number. So Avogadro's number is the other name that we can call a mole, because it was named in reverence of an Italian scientist whose last name is Avogadro, and we'll get a look at him later. But I do want to say it is named after him, not because he discovered it. So we'll talk about him in a little second, but just know we can call it Avogadro's number, even though it's not for the work that he did to discover this number. That's incorrect. So here's a little picture for you. Each of these little weigh papers, so the papers that these substances on, would probably take up about the size of a palm of your hand. So on each of these weigh papers, there is 1 mole of the substances that they represent. So in the top left corner, that's zinc right there. So if that's 1 mole of zinc particles, it means that there are 6.02 times 10 to the 23rd particles of zinc on that paper. And it's smaller than what you could hold in your hand with those tiny little zinc filings. You can see that all of these substances, there are only 8 listed on here, but you can see that all of them clearly occupy different masses as given by the weights represented in grams, and they clearly occupy different volumes as they take up different amounts of space on those weigh papers. But the thing that they all have in common is that there is 1 mole of those particles of that substance. So there's 6.022 times 10 to the 23rd particles of zinc, and there are 6.022 times 10 to the 23rd particles of copper, and all those other ones that you see represented there. So I will show you some more of these in person, but I just kind of want to give you an appreciation for like the fact that even though they have the exact same number of particles, they occupy different masses and they occupy different volumes. So take a look at this little tab right here. This is the elemental symbol for carbon. We're going to analyze this really quick to kind of pick out some information from it. So first things first, what does that 6 represent in the top left-hand corner? And the crowd says, atomic number, Miss Lambert. Yeah, so it represents your atomic number, which means the amount of protons you would have in a carbon atom. So what about that 12.011 number? Well, we've previously learned that that 12.011 number represents the average atomic mass. So what that means is there's a lot of different isotopes or a lot of different versions of carbon atoms where every carbon atom has 6 protons but different numbering neutrons, therefore making the masses of all of those isotopes different. So how did they pick which number went on the periodic table? It was all about taking the mass of all of the isotopes of carbon, averaging it out and throwing it on the bottom of that element symbol, and that's the one that we use on the periodic table because it is our best representation of any single carbon atom. So it's not saying that all carbon atoms have a mass of 12.011. It's saying that if you were to grab any one carbon atom, its mass is likely around that number because it's a good representation based off of the abundances of all of the different isotopes of carbon that exist. So why am I talking about this? Well, it turns out that that number that you see on the bottom of that element tab, 12.011, while it is the average atomic mass for a carbon atom, you can also refer to it as the molar mass. So what this is saying is if you had 1 mole of carbon atoms and you put that onto a scale, the scale would read 12.011 grams. So the molar mass refers to the mass per mole for each substance. The ones that you see on the periodic table are the mass per mole for each element. So if you had 6.022 times 10 to the 23rd atoms of carbon, it would weigh 12.011 grams. I'm saying this a lot of different ways, but they're all saying the same thing. Remember how we talked about how you have to hear things a million times, or like 50 times plus in order to get it in your head? The more I say this to you, the more I hope it goes in. So that number, we call it the average atomic mass. If it shows up on the periodic table, we can also call it the molar mass. So pause to take a second here and see if you've got it. What would be the molar mass of calcium? 40.078 grams per 1 mole of calcium. That's exactly right. So what this is saying is that if you had 1 mole of calcium atoms, 6.022 times 10 to the 23rd calcium atoms, it would weigh 40.078 grams. Okay, amazing. So that brings me to this cutie right here. So this is a picture of Avogadro. His full name is Lorenzo Romano Amadeo Carlo Avogadro. He is an Italian fella who actually was a lawyer. And then he became interested in math and physics, and then eventually he became the first professor of physics in Italy, which is really interesting. So Avogadro did a lot of work in the physics and in the physics field involving gases, and that's kind of where like physics and chemistry overlap. It's called physical chemistry, and it's kind of as if physics and chemistry had a baby. So that's kind of where Avogadro was hanging out. So Avogadro did a lot of experiments with gases, and he kind of first hypothesized that if you had some amount of gases, you had equal volumes of them, but they were at the same temperature and pressure, then they should have the same number of particles that occupied that space, occupied that volume. And a lot of people thought that he was like kind of crazy and that was a wild idea and nobody really believed him. And it turned out later that he was actually right. So that's why when the next person who kind of came along and used this idea actually found the numerical value for the number of particles in that space, he named it affectionately after Avogadro. So the person who actually discovered Avogadro's number was a French physicist named Jean-Baptiste Perrine. I think it's Perrine, but I don't know French, so I don't know where the accent is there. But he essentially is the first person to hypothesize the value of Avogadro's number, 6.022 times 10 to the 23rd. So how would we actually use this number? Why do we care? Really what Avogadro's number is super good for is it's used as a method of unit conversions. So we can convert between different units of substances. If I know that I had 6.022 times 10 to the 23rd particles of that substance, I would be able to do some unit conversions to get different values in terms of like masses or molecules. Units for Avogadro's number, you can talk about atoms, you could talk about molecules, you could talk about electrons, ions, so many different things, because really, again, all it is just a counting unit. So if I were to say you had 2 molecules, you could also say you had a pair of molecules. If I said you had a mole of molecules, you would know that you had 6.022 times 10 to the 23rd molecules. So we are going to use this a lot in terms of unit conversions when we get to later units. For right now, what we really need to be able to calculate is molar masses. So Molar masses are not just for elements. If you look up on the periodic table, that is the mass per 1 mole of that element. But you can deal with a lot of different stuff. You can deal with a bunch of different formulas in terms of like compounds. You could use compounds, you could have plain old elements, you could have diatomic elements, which are those elements that come in pairs. So to do this, it's actually a relatively simple process. Really what you're gonna need is a periodic table, and you're gonna need a calculator so you can add some stuff up. So I'm going to walk you through an example of how you can find the molar mass of a compound, and then I'm going to have you do one example on your own. So the example that I'm going to share with you is for water, H2O, because water is a good old pal, nice, friendly molecule. So step 1 for determining molar mass of a compound is to pick out the elements you have in that compound and find their individual molar masses on the periodic table. So if you look at a periodic table, you'll notice that for hydrogen, the molar mass is 1.008, and the molar mass for oxygen is 15.999. Tap. There we go. So what we're going to do first is just find the molar masses for one atom of that individual element. Step 2 then is going to be to figure out how many atoms you have inside that compound. So for water, I have 2 hydrogens and I have 1 oxygen. So I'm going to take the molar mass for hydrogen, 1.008, and I'm going to multiply it by 2. So this tells me that the weight of hydrogens in that molecule is 2.016 grams per mole. Same thing for oxygen, I just multiply it by 1, so I keep the exact same thing. Now for step 3 is you add them all up to find the total molar mass for the compound. So when I do that, you would get 18.015 grams. So this is saying that if you had 1 mole of water molecules, or 6.022 times 10 to the 23rd water molecules, it would weigh 18.015 grams. So let's have you practice now. You're going to now do an example for lead 4 bromide, PbBr4. I'd like you to take a stab at finding the molar mass for this compound, and then you're going to go ahead and check in with the answer key, and then you are finally done with this lesson. Bye, everyone.